Sushruta for NEET is now available on the Google Play Store. Try it out for free.
I also I felt that today I should do some of the remaining ideas that we were pursuing in heat. Kind of wind it down. Okay, I was actually looking to wind it down last week, but then see, I felt I had not done enough justice to a couple of topics. Okay, so I am going to do a little more justice to those two topics, and so please bear with me. So first, I'm going to discuss today. Let me share my entire screen so that I can. Usually, that seems to work better these days. All right. So today we will discuss the thermal properties of matter. And this is a very basic idea, but it's actually a very important idea. And your understanding of physics as a class 11 student should be shaped by some of the things you learn in this and some of the things you learn in chemistry, notably physical chemistry. So these things, they are correlated and related, so that's why we want to do justice here. So now, as you know, the main advantage with using the Jnanamarga platform is that you get IIT PAL in your ebook along with our high quality slides, and you can watch videos and then attempt questions. Okay. What is the advantage with that? The advantage with that is everything is integrated. It's an integrated study platform, and everything comes from that one integrated studying platform. So if you are a Sushruta for NEET person, you're going to be taking the NEET, 2 years from now or 1 year from now. This is a perfect time to get your full system in place. Now we also deliver the tablet version for students, and the tablet version for students comes with full slides for all subjects. HC Verma as an ebook, A to Z books, and then the NCRT books as well. And then we also provide, we have this set of live lectures, and then you can work with the tests that we do have, as well as the mock test. So we have a full platform, but our physics story is always enhanced by the work that you do. And what we try to do is we try to get students to study from concepts of physics and then follow along with us through HC Verma. Okay, so that is a very important. Now for the JE students, this is even more important. Physics is only a quarter in NEET, but it is about a third in JE, and very often the maths is tough. The chemistry you can do well, but the physics is what makes a lot of difference, because that's where conceptual application really builds you a very high score. Okay, so maths is tough, but you must study hard for maths, and it's a skill. But the students who do well in physics, invariably get high JE main score and then make it into a quality institution. Lot of schools now. I saw yesterday that JE mains is accepted into a lot of colleges in West Bengal, and also preparing for using our class 12 material particularly helps you, like if you are going to be taking good set, or if you are going to be in one of those competitive exams for engineering. So Ramanujan for JE helps you, and then you have additional opportunities. So heat is like a form of energy that is transferred between two systems. Okay, heat and work, as we discussed last time, are related by our study of thermodynamics. But heat and temperature, as we also discussed, is are is very intricately related. Temperature is a property of a particular material. It is an intrinsic property. Okay, so so in common, so you have liquid on in glass thermometers, right? So now when you do these conversions, temperature conversion should be very simple for you. Tf minus 32, right, times 9 by 5 will give you Tc. That times 5 by 9 will give you Tc. Tf is what? Fahrenheit. So 100 degrees Fahrenheit, 100 minus 32 is 68. 68 times 5 by 9 is what? 68 times 5 is 6 fives are 30, right? 34, 340, right? 68 times 5 by 9 is 340 divided by 9. 340 divided by 9 is what? Almost 40 degrees. 38 degrees. So 38 degrees centigrade is roughly um, 100 degrees Fahrenheit, right? So now in India today, we are hearing of temperatures in which are almost 45, right? 45 is what? So you just take 38, you add 7 more degrees, 7 times 9 by 5. 7 times 9 by 5 is what? 63 by 5 is almost another uh, 10 11 degrees, right? So 11 12 degrees, right? So 112 degrees, 112 degrees in the hot sun, right? When it's 45 degrees. So that's a very hot temperature. Now, we all learned a Boyle's law and Charles' law. PV is a constant, V over T is a constant. So PV equals nRT, right? PV equals nRT is what we call as the ideal gas equation, and we will be looking at that. Now, this is PV, this is essentially what? This applies only to gases, right? Don't ever forget that, right? PV equals nRT is a gas law, ideal gas equation. Okay? Now, solids and liquids also expand with heat, right? But not as much. Okay, you don't have the same level of expansion. It expands a little bit. Water has this very funny expansion. We will discuss that now. Coefficient of when you have solids, right? We have what is called the coefficient of expansion. Okay, you have coefficient of linear expansion, delta V by T, right? Delta V by V, right? Is so we when you have volume, right? Coefficient of volume expansion, you have it's called alpha V is delta V by V times the coefficient of volume expansion is how much has it expanded for each degree increase in temperature. So if the temperature goes up by 1 degree, the volume expansion will be this many percent. Okay, so delta V by V is the percentage increase in volume, right? So the corresponding increase in volume will be this much. Okay, so delta V by V equals 3 times, and basically what you can say is that because it's a linear expansion, volume expansion will be 3x that. So 3 times the linear will be the volume expansion. So delta V by V, right, equals a constant times delta T, and that constant is alpha V, right? So alpha V times delta T, right? So similarly, you have delta L by L equals alpha times delta T. So this is the coefficient of linear expansion. This is the coefficient of volume expansion. Coefficient of volume expansion will roughly be 3 times the coefficient of linear expansion, right? So if and why is that? That is merely calculus. Merely calculus. V, what is that? V equals L cubed, right? So dV by dL equals 3L square dl. 3L square, right? So now You divide both sides. So dv equals 3l square dl, right? So you divide both sides by v. On the left side you put by v, on the right side you put l cubed, right? So now you end up with dl over l equals 3 times dl over l equals dv delta v over v. So that's where the 3 comes from, 3l square dl. Okay, so v equals l cubed, so 3l square dl. Now what essentially happens is that your if your expansion was proportional to the temperature, right? It was linearly proportional to the temperature. That is, you have coefficient of linear expansion being, so L equals delta L over L equals alpha L times delta T. Then your corresponding case, when you have volume expansion, you will end up with that 3 number, right? So delta L over L is what? DL by L, right? 3L square means by L cubed is what? L square by L will 1 L will end up will be left, right? So 3 times DL over L equals delta V over V, right? And DL over L is what? DL over L is alpha L times delta T. Okay, so 3 times alpha L over delta times delta T equals dV over V, which is on the left side. So V equals L cubed, and you have that, and then on the other side you also have delta L over L equals alpha L times delta T, right? That is the coefficient of linear expansion. So for each degree increase, you will have a linear increase in the, so that is the linear relationship. Okay, delta L over L equals alpha L times delta T, right? So delta L over L is what? It's a alpha L. Yeah, or delta L over delta T equals alpha, right? So you therefore have that linear growth, right? Linear growth is what? So you have, for each increase degree in temperature increase, you have a fixed increase in the length. So that is the main idea there. Okay, so let me continue with that. So what happens? The volume grows thrice as much for each degree in temperature, right? Because you have an area grows twice as much, right? So if you look at it, if the length grows by this much, the breadth grows by this much, you have 1 and 2, right? And similarly, the volume has a 3, right? So if this grows by a small delta L, this will grow by delta L, and this will grow by delta L. Therefore, you will have the area will grow by 2 times. Okay. So, and the volume will go by 3 times. Okay. So that's how you have 3 times alpha L. Okay. So keep that in mind. Now, water, as we discussed, has anomalous expansion. It has its greatest volume, right? Its density is least at 4 degrees centigrade. It then decreases as for all temperatures from 4 to 100. At 100 degrees in under normal temperature and pressure, water becomes gaseous, water vapor, right? It boils, right? Now, below 4, what happens to water is it again expands, and then at 0, it becomes ice. Okay, so this expansion between 0 and 4 degrees, right? Normally, if you keep decreasing temperature, it should keep going, becoming smaller and smaller and smaller, right? According to this, right? Linear coefficient of linear expansion. But water between 0 and 4 degrees expands. That's why ice floats on water when you drink your Fanta or you drink your Coca-Cola. Remember, the the ice floats at the top. Okay, so that's my general point to you. PV equals nRT, where n is the number of moles, right? And T is the absolute temperature. Now, P delta V equals mu mu times R times delta T. There, that's how we have this derivation. Okay, so delta V by V equals delta T by T for ideal gas. Therefore, so uh, I explained this derivation to you. V equals L cubed delta V equals L plus delta L cubed minus L cubed. So you therefore have 3 times L square delta L. The delta L cube term disappears, as does the delta L square term as well. So now you divide, and therefore you have delta V by V equals 3 times delta L by L. Delta L by L is alpha L. Okay, so coefficient of alpha is 3 times coefficient of delta. Okay. Now, thermal stress is what develops in as a result of that expansion. Okay. Now, the expansion is related to alpha L, right? But that expansion, so when you have when you expand something, it produces stress over strain. Stress over strain is what? Young's modulus, right? So the delta L over L is given by alpha L times delta T, right? Alpha L times delta T leads to a corresponding stress. Stress is what? So y times stress over strain is a constant. That constant is called the Young's modulus, right? This is the simple law, right? Young's simple law, Young's modulus, right? Stress over strain, right? So and stress is what? Force per unit area, right? Force per unit area, same as pressure, right? So from that you can calculate. Okay. So now here's a simple question. Pendulum has a copper rod kept which keeps correct time at 20 degrees. It gains 15 degrees to 15 seconds per day if cooled to 0 degrees. Why is that? 2 pi times root of L over G. G doesn't change. What changes is L, right? So what is the corresponding L, right? L equals L naught times 1 plus alpha times delta T. Delta, or the change in temperature, right? Change in temperature is 20 degrees. So when your L goes down, right? When your copper rod when the if cooled it if cooled uh, 20 degrees, it's the length is going to decrease, and when the length decreases, the period is going to decrease. So if the period decreases, it's going to go faster. Okay, the number of seconds that it's going to do is faster, right? So now the coefficient of linear expansion of copper is given by what? Right, is given by alpha here, right? So so what they are saying is that corresponding to a 20-degree increase, right? Now what is going to happen to the square root of L? Square root of L introduces this other 0.5 term. Okay, so delta theta, right? So you can do it any which way you want. Okay, so now if it gains 15 seconds per day, right? So T 20 degrees minus T0 by T0, right? So if it gains 15 seconds per day, what does that mean? It's instead of day has 2400 times 24 times 3600, right? 24 times 3600 seconds. Now if instead of having 24 times 3600, it has an extra T20 minus T naught, right? T20 minus T naught is what? So T20 is, it does 15 more actions, right? So T20 minus T naught is 15, right? And 15 divided by T naught is what? T naught is a day, right? 24 times 3600, right? Therefore, so from that, and then theta is 20 degrees, right? So now, um, the idea here is the variation. So if you look at this, right, t equals 2 pi times root of L by G, right? Now if you take the derivative, right, delta t over delta L equals half L to the power of half is half L to the power of minus half, right? And therefore you end up with the L to the power of half going into the denominator. Okay. Uh, and so that times dl by dt, or dt by dl, right? Dt by dl equals half L to the power of divided by. So you end up with a L to the power of half in the denominator, right? And that can be written as in terms of t. Okay. And the 2 pi and g will cancel, right? So you will end up with by t on left hand side, and the L to the power of half will become L. You'll have an extra L, right? So, um, and therefore you will end up with this zero point 0.5 in this on the right hand side. So T naught will have a zero point 0.5 times alpha times delta theta, because uh, the length expansion is linearly proportional to temperature change. Okay. Now, but then we are not interested in the expansion of length, but in the square root of that. So that's why you end up with half 0.5. We're interested in the square. We saw it becomes 2l, right? Now, because we're interested in the square root, it becomes 0.5. I'm talking about this one, right? This one. 3 times L, right? So instead of alpha V, we are looking at alpha L to the power of half, right? Alpha L to the power of half is half times alpha L, similar to the volume expansion and the other. So that's the important idea there, right? So you take the derivative, you end up with a equation there. So these expansions are dictated by the ratio, the corresponding ratio. So V equals L cubed. In this case, V equals L to the power of half. T equals L to the power of half. T is the period. Okay. So that is the deciding factor. Okay. Now, specific capacity, heat capacity is the change in temperature, a given amount of heat is absorbed or given away by the body, right? So if you had specific heat capacity, right? So all these problems with specific heat capacity, typically the most important thing you have to do is heat lost equals heat gained, and that is the central idea. And so specific heat capacity is delta Q by delta T. Now, heat capacity is delta Q by delta T. Specific heat capacity is delta Q by delta T per unit mass. So you have delta Q by M delta T. So Q equals MS delta T. Or delta T is the temperature. Q equals MS delta T, you must remember. Okay. So now if you, instead of specific heat mass capacity, it is per unit mass. If they gave it to you in terms of moles, then you must use correspondingly molar specific heat capacity. So it is given on a per mole. Okay. And so calorimetry problems always involves this heat lost equals heat gained, and you must use that. So here they put a gold sphere is placed for sufficient time in a water, boiling water, so that it is 100 degrees. It is then transferred to a calorimeter. So when you keep it in a boiling water container, so that the gold becomes also 100 degrees, right? So 0.1 times 100 degrees, right? So zero point 0.1 times 100 degrees, then it kept in water, and the resultant water is 0.25 steady state, right? So now the gold has lost how much temperature? 0.1 times specific heat of gold times 75 degrees. That is the heat lost by the gold. It is the heat gained by the water and the vessel, right? So the vessel gains 0.2 times 5 degrees times specific heat of copper, which is 4180, plus point, plus 5 degrees times the weight of the water is what? Right? The water is, 0.25. 0.25 times 5 degrees times water. So 0.2 times 1000 is the copper, and times 5 plus 0.25 times 4180 times 5. Okay, so that is the both go from 20 degrees to 25 degrees. That's how you end up with the pi. ms delta theta equals ms delta theta plus ms delta theta equals gold ms delta theta, where delta theta has gone down 75 degrees, right? So heat loss equals heat gain. Then you solve for the now change of state. You have these what are called state change diagrams, phase diagrams, right? So there is a triple point which happens at a particular pressure and temperature. So phase diagram happens at different pressures and temperatures. At low pressure, things convert directly from vapor to solid. Okay, under now if you keep increasing the pressure there is a when you go from when you keep decreasing the temperature, it will go from this is what happens with certain substances. It will become liquid and then it will become solid, right? Like water. But some substances go from vapor to pressure to solid, you know directly. Okay? And there is a point when all three can exist. Okay? And that point is called the triple point. Now liquids also have a supercritical presence, including, and if you keep increasing the pressure, okay, supercritical is ultra supercritical, etc., is based on how much pressure you put. Okay, so but remember this picture, right? So this is called sublimation, is when something goes from solid to gas or other way. Okay. Now, otherwise, it goes for you have this idea of going from gas to liquid or liquid to gas, and then from liquid to solid. You can't go directly to solid, right? Except if you reduce the pressure. Okay. Now, latent heat is what happens when something changes state. So, if something changes state, Q equals M times L. So, latent heat transfer at the same temperature, it will then switch from one mass to for one form to another. So when quantity of ice is mixed with water, what happens? You have latent heat, right? Heat loss equals heat gain. Heat loss is M times L, etc. The heat gain is ms delta heat. Okay, so these kinds of examples will come. Heat loss equals heat gain is very, very important. Okay, so very simple questions you should know how to handle. Okay, now finally, the other thing that I wanted to go over was this kinetic theory of gases. Okay, kinetic theory of gases is not very straightforward, and you must spend some time reading the book. Okay, now in kinetic theory of gases, you understand how an ideal gas will behave. Okay, ideal gas behaves. You make some assumptions and then you prove the properties of the ideal gas. Okay, that's how you end up with that 3RT, square root of 3RT by m, etc. Okay, now you have a cubic box, which we discussed in the context of that Boltzmann law, right? Boltzmann law statistical model, right? Now consider a cubic box of length 1, and then in that box you have these particles moving back and forth. Now, when it hits the wall, it collides and then it gains momentum. It goes, hits mv times x, it bounces right back with it's a elastic collision. There is no loss of energy. In an elastic collision, there is no energy loss. There is momentum going this way is mv, momentum reversing is this way mv, right? So, what is the change in momentum? 2 times mvx. Okay, now so you have a square box of length 1, therefore you have this continuous back and forth that happens. Now the force change in momentum times time dp by dt is force, right? Dp by dt is force, right? So now the time is the distance by speed, right? So now goes this way once, comes back this way. The time is 2, the distance traveled is 12, the velocity is vx. Let's say it's a velocity in this direction is like this, right? So the force is the change in momentum divided by the time taken. Okay, so therefore dp by dt, right? So force is 2 times mvx, that is the change in momentum, divided by this time, right? 2 times mvx divided by 2l over vx. Okay, so then you therefore end up with mv square times l. Okay, therefore now the what is the pressure? Pressure is the force per unit area. I think I should get these things right, right? Force per unit area, right? So and that's how we should be looking at it, right? So uh, and um, force per unit area, right? So so the pressure is, so dp by dt, dp by dt, right, is therefore you then have dp by dt, and dp is given by 2 mvx, right? So dp is given by 2 mvx divided by 2l over x. dp by dt is given by, therefore have 2 mv x over 2l over vx. What? So this is equal to, two twos cancel, mv square over l, right? mv square over l, right? So that is your force. So now you have three different dimensions. So the pressure is force per unit area divided by L square, right? So mv square over L cube, right? So mv square over L cube will give you your pressure, force per unit area. Now, so you do mv square over L cube and you have three dimensions. Therefore, there are three different directions. So mv square, so the pressure is ends up becoming um, 3 times mv square over L cube. Okay, and therefore you have vx square plus vy square plus vz square equals v square. Okay, so the average velocity is related to v, right? Therefore you therefore end up, when you substitute these equations, you end up with this important equation with respect to pressure: n mv square times this. Okay, so 3 times 1 by 3 times nmv square. PV was 1 by 3 times nmv square. Okay, so you end up with that equation: 1 by 3 nmv square, where m is the mass and n is the number of molecules. Okay, so PV equals 1 by 3 nmv square. So that lays the foundation of your, and PV equals nRT. And therefore, you cancel out the, that's how you end up with 3RT over n. Square root of 3RT over n comes from this equation. So you write PV equals nRT here. You will then end up with nRT equals 1 by 3 nmv square. Nn will cancel. Therefore, you have 3RT over m equals v square. Okay. Therefore, from that you get the average velocity. Okay. This is a simple derivation for the average velocity. Now, using all this, we can then integrate all these into these various equations that we have with, kinetic theory of gases. Okay. So you have the specific heat capacity, which deals with solids, and with so ms delta 3, or with liquids, specific heat capacity of substance, the amount of energy required to raise the temperature of 1 kg by 1 degree. So ms delta theta equals delta q, right? We have all these specific heat capacities, right? So you see here, p, and then you have also the enthalpy equation. Okay, so you have the enthalpy equation. H is the enthalpy. Enthalpy is E plus PV. Enthalpy is E plus PV, right? Where E is the corresponding, so from the law of thermodynamics, H equals E plus PV, right? And the equation of state, PV equals nRT. Therefore, delta H equals delta E, where E is the internal energy plus P delta V, right? And P delta V equals R delta T, right? Therefore, delta H equals Cp times delta T. Okay, so the enthalpy. So remember this equation: H equals E plus PV. E is the internal energy, right? So delta H equals delta E plus P delta V. P delta V equals R delta T. PV equals nRT, right? And therefore you have delta H equals Cp times delta T. Therefore Cp equals Cv plus R. What does that mean? Cp is the heat capacity, okay, and Cp equals Cv plus R. R is the uh, uh, heat constant, gas constant, right? Cp equals Cv plus R. Cp is what? The heat capacity, right? So, and it is the heat capacity associated with enthalpy. So, so keep that in mind. Cp equals Cv plus R, and you can define the ratio Cp over Cv with gamma. You may remember PV to the power of gamma equals constant, right? And so now we will discuss this other term called equipartition of energy. So you have 3 degrees of freedom, right? Sometimes you have many degrees of freedom, okay? Beyond 3. Now, for each degree of freedom, you have a half kT. Each degree of freedom will contribute a half kT to the energy of the system, where the possible degrees of freedom are associated with translation, rotation, and vibration. Normally, translation you have X, Y, and Z, 3, right? But then you can also have rotation. Then you can have vibration. Okay, so gaseous particles can rotate, vibrate, and also translate. So you have multiple degrees of freedom, and each degree of freedom produces you a half kT. So if you have 6 degrees of freedom, you will have 6 times half kT. Okay, and therefore we introduce this term called mean free path of a gas molecule. Like so, following are the mean free path factors: the density, the radius, and the number of molecules, temperature, and pressure. Okay, so multiple factors affect the mean free path of the molecule. This is very well explained in Professor H.C. Verma in his book. My suggestion is that you read this kinetic theory of gases chapter in chapter 24 of book 2. Okay, so kinetic theory of gases is taught very well there. And I would ask you to take some time to understand the assumptions of kinetic theory of gases, and also how it deduct the deductions of the kinetic theory of gases. Notably, this discussion with respect to the mean free path. Okay? And so this is a very important idea that you should learn. Okay. Now there are 6, 7 chapters in heat, and kinetic theory of gases is one but very important factor. Okay. So so please feel free to make this work well. Okay. So the mean free path of a gas is given by this complicated formula, and so it is dependent on the density, the radius of molecules, and the number of molecules. Okay. Now, uh, this is a more complicated thing. I don't think this is very useful, Leonard. But the non-ideal gas equation, the real gas equation, this is very useful. Okay, so just give me one minute. Okay. The real gas equation is extremely useful. Okay. Um, um, why is the real gas equation useful? Because a lot of gases behave using according to this real gas equation. Okay. Why and this real gas equation is given by this P plus it's called van der Waals equation. Okay? Instead of PV equals nRT, you end up with this P plus V by N minus B equals nRT plus this very complicated second term. Okay? So the pressure is affected by this term and the volume is affected by this term. And so PV equals nRT changes very quite differently. This is an adjustment to the pressure, and this is an adjustment to the volume. Okay, so and so the for each more there is an excluded volume of radius equal to the molecular diameter. Okay? So that is how you end up with this, and therefore you have this B is measured in cm cube per mole and called excluded volume or co-volume. The B in this term is called co-volume. It is removed. It is the excluded from the volume. Okay, so that is what decides that in van der Waals equation. There is a correction of the attractive forces. So the corrected P is this one, right? You have this one P plus n square A by V square. So this is the P correction, right? And this is the excluded volume. Okay, so you correct for the pressure and you correct for the volume in van der Waals equation for a real gas. Okay, so now isotherms, they behave in certain ways. Isotherm is what? Constant temperature. What happens at a particular constant temperature? The PV equals nRT. You normally have PV equals nRT means it will be a parabola, right? PV equals constant is a parabola. But in real terms, it goes like this, has very funny behavior, and that is partly complicated by the fact that they go from one form to another, and then they have this van der Waals forces in play. So I'm going to stop here, but I'm going to ask you to a little bit read the chapter in HC Verma, because this is a very complicated discussion, and we are not having this discussion here. Okay, so the real gas equation is little beyond the scope of what you will be questioned on in in your subject, but you should know roughly what they're talking about. What is van der Waals force, and there are weak forces that exist, and then you have an excluded volume and you have a corrected pressure, right? And therefore PV equals nRT changes to reflect this particular equation. Okay, so with that, I'm going to stop. So this is our last class before we start the new semester. Next class onwards, we will be starting the new semester. Okay, so and I'm going to end here, and then we can discuss the new semester next week. With that, I'm going to end, and we'll speak again later. Thank you.